Hey kids, so far we've been doing linear and dealing with linear differential equations. So now I'm going to show you how to solve nonlinear differential equations, sort of, right? So nonlinear differential equations creates a lot of headaches. So I'm going to give you a type of nonlinear differential equation that we can manipulate into solving. So the integrating factor method, you remember, is what we used. Where did it go? The integrating factor method is what we've used to solve the linear differential equation of this form, right? Where we had y prime plus, and remember that p of t could be a constant. In that case, our integrating factor was just e to the constant times t. Or if it was actually a function, then the integrating factor was the integral of e to that function. Right? So if we recognized this or could manipulate ourselves into this form, we could use the integrating factor method. What that means is there is an assumption that p and g are continuous functions, and if that is so, then we can definitely find a general solution, which is just our plus c, and if we're given an initial condition, we can solve the initial value problem and get a particular solution. Nonlinear differential equations pose a lot of problems. So let's try to recognize some cases where we can deal with them. So the whole idea, and hopefully you got used to this in multivariable and now in differential equations, this whole idea of using a bunch of algebra, right? Algebra and calculus tricks to transform things. In multivariable, we transformed our space, right? And now we're going to be using algebra and actually transforming our equations. So notice what's different about the equation that I just wrote down and what we have been dealing with. Do you see it? Well, firstly, I changed the G to a Q. I don't quite know why to do that, but it doesn't really matter. What matters is there's a y to the n, right? I have y prime over here, I have y here, and I have a y to the n here. This is called Bernoulli's equation. There he is. There's three Bernoullis, and I always forget which one is which. There's an uncle and a son and a nephew, or I don't know, something like that. I forget. Now, if this power on y over here is either 0, so you have a constant, or 1, we still have a Bernoulli's equation, but we don't need to convert it. Right? This is a Bernoulli's equation. It's just that it has a y to the 0 here, right? So if I have a y to the 0, I just have a y to the first, I'm still dealing with a linear differential equation. I don't need to convert it. But if n is 2 or above, and I am talking about n being integers. Oh, I forgot. We don't need to convert, just use the integrating factor method. Don't need what, when I say Bernoulli's, I think of when n is greater than 1. And that's when I use what I think of as the Bernoulli method. So this is how we do it. So I'm going to do this in general. I'm not going to put a number in for n. I'm just going to leave it in general first, and then I'll do some equations where I put a power in for n. So the first step is to get that right side without any y's. So divide both sides by y to the n. And then look how I'm going to algebraically rewrite that. Obviously, this y to the n goes away, so I am just left with the function over here on the right. And then on the left, y prime divided by y to the n, look how I wrote it. Right, just 1 over y to the n. And then look what I did here. Right, this is y to the first. Y to the first divided by y to the n is y to the 1 minus n, right? That's just your exponent rules, right? Now here comes Bernoulli. Decide or rename this y to the 1 minus n as v. Call it v. Then take the derivative of both sides of this equation with respect to x. So take the derivative of v with respect to x, which means you're going to do implicit differentiation here. Right? You're going to bring down the exponent, 1 minus n. Here's the exponent. Bring it down in front, copy over the y, subtract 1 from the exponent. What's 1 minus n minus 1? Well, it's negative n, isn't it? Spit out the derivative of the stuff, the derivative of y with respect to the variable I was differentiating with. Now, do some algebra. See what I did there? I divided both sides by 1 minus n. I divided both sides of this equation by 1 minus n. And then I rewrote y to the negative n as 1 over y to the n. And then look at this red box. So this red box is step 2. This red box is step 4. Replace. So 1 over y to the n times y prime. I substituted, right, because it is equal to 1 over 1 minus n v prime, or dv dx. Then I had my plus function here, plus a function, and then replace y to the 1 minus n with v. I'm almost there. Multiply everybody by 1 minus n, and I have a linear differential equation. Oh, snap. Then I can use the integrating factor method on it. Right? Pretty good. Right? Because remember, n is just a number, so this is going to be just a constant, right? Constant multiple. Constant multiple. All right, let's do one. So I have a differential equation where on the right side, this is nonlinear. Nonlinear differential equation. I do have a y to the first, but over here I have a y cubed. So what are you going to do? Divide both sides. My 3 is the n. Divide both sides by y cubed. Y cubed divided by y cubed is 1. Y to the first divided by y cubed is y to the 1 minus 3. So that's what you're going to name v, step 2. Differentiate both sides. 1 minus 3 is actually negative 2. So bring down the negative 2. Y to the 1 minus 3 is just y to the negative 3. Spit out, right? This is implicit differentiation. Do a little rewrite, little algebra. Divide both sides by negative 2. Write y to the negative 3 as 1 over y cubed. Of course, you don't really have to do that if you see it, right? And then substitute. Almost there. Multiply everybody by negative 2. Now I'm down to a linear. Right? Linear differential equation of the form, right? A derivative plus a constant. There's my constant times v, right? That's y prime plus ay is equal to g of t. So now I'm going to use the integrating factor method. Bam, bam, there you go. Right, the integrating factor method. Here's my integrating factor, e to the negative, right? Where'd that negative 2 come from? Right, that's my a. A equals negative 2. So I took the linear differential equation and I multiplied through by e to the negative 2t. That's this step. Recognize then that this was the product rule of e to the negative 2t times v. Integrated both sides. So I got e to the negative 2t v is equal to integrated negative 2 e to the negative 2t. So I got e to the negative 2t divided by negative 2, but then that negative 2 as the multiplier here went away, plus c. Trying to get v by itself, so I divided everybody by e to the negative t here, or same thing as multiplying by e to the positive 2t. That got v by itself. Once I had v by itself, I replaced, right, what v was equal to. V was equal to y to the negative 2, which is the same as 1 over y squared. reciprocated. Didn't bother getting y by itself. I'm done. And I'm in my solution, right? I have a fraction, so I'm a little bit worried about division by 0, but nothing is going to make that 0. Good? Let's do one more. This is a differential equation. There's a derivative, but it is nonlinear. Divide both sides by y to the 4th. Whoops, I dropped an x there, didn't I? That's why I have just an x there. Y to the 1st divided by y to the 4th is y to the 1 minus 3. Take the derivative with implicit differentiation, bring down the negative 3. Do your replacement. Multiply through by negative 3. And you have your linear differential equation, where you are now going to do the integrating factor method. Where a is equal to negative 3. Therefore, your integrating factor is e to the negative 3t. Good? Good. I'll let you do that part yourself, or we'll do it together in our live session. And we'll also, in our live session, do some of these when we have an initial condition, and we'll talk about making sure that our solution is valid. All right? I'll see you in our next live session.